In this video, we want to take a look at another type of proof method. These are called proofs of induction or inductive proofs. So simply put, the principle of mathematical induction says, let's say we have a proposition S of n whose domain is the natural numbers. And let's suppose that S1 is true. Then for all n bigger than 1, if Sn is true, then S of n plus 1 is true. Now, the idea when we do proof by induction is we want to show that the base step S1 is true. So show that it can be done perhaps for a really small number. And so these inductive proofs are generally used when I wish to prove that a formula for something exists and is what it is. So the base step is to show that S1 is true, and then the inductive step is to assume that the formula works or that Sn is true for all n. And if I can show then that S of n plus 1 is true, then in essence I have proven my result. Okay? So what we want to do is we want to do a couple of examples. I want to compute the sum of the first 100 natural numbers. So if I did this, okay, the long way one plus 2 plus 3 all the way out to 100. Okay, I could grab a calculator and I can add those up for a really long time, and that would just be kind of a tedious exercise. However, I could look at it as follows. I could notice that if I arrange these natural numbers 1 through 100, and then I reorder them, so 100 plus 99 plus 98 all the way back down to 1. And then I added these two together. So adding, I would get 1 plus 100 is 101, plus 2 plus 99 is 101, plus 3 plus 98 is 101. And if we notice, each time I compute a sum, I get 101. So that's nice. I get 101 100 times. The issue with this, though, is that this sum is twice as large as what I want it to be, because I didn't want to do 1 plus 2 plus 3 all the way up to 100 plus 100 plus 99 plus 98 all the way back down to 1. I really just want to do 1 to 100. So the idea is I would take this product, divide it by 2, and we end up with 5,050. And so this leads us to this idea that possibly this little formula right here might be able to be used to compute the sum from 1 to 100. So 100 times 101 divided by 2. So Part B says I wish to use induction to show that the sum of the first n natural numbers is n times n plus 1 over 2. And this is a classic example of proof by induction. So let's see if we can't do that. So proof 1 plus 2 plus 3 all the way out to n is equal to n times n plus 1 over 2. So proof by induction, the base case or the base step, show true for n equals 1. So 1, does that equal 1 times 1 plus 1 over 2? Well, that's 1 times 1 plus 1 is 2 over 2. That's 2 over 2, which is 1. So sure enough, that works. So now we have what is called the inductive hypothesis. And so we get to assume that this is true for all n equals k. That is, assume 1 plus 2 plus 3 all the way out to k is simply k times k plus 1 over 2. And this is what we are going to call the inductive hypothesis. Now, the last step is called the induction step. And so we now show that this is true for k plus 1. That is 1 plus 2 plus k plus 1 would equal to, well, what does our rule say? What does our formula that we're trying to prove say? To find the sum of the first k integers, it's k times k plus 1 over 2. Well, if I want to find the sum of the first k plus 1 integers, well, then my induction step would be k plus 1 times k plus 2 over 2. So the idea is I wish to show that this is true. Now, 1 plus 2 all the way out to k, this is my inductive hypothesis. So by the inductive hypothesis, this sums to k times k plus 1 over 2 plus k plus 1. I still want to check, is this equal to k plus 1 times k plus 2 over 2? Well, let's check. Okay. If I were to multiply all terms by 2, so I'm going to multiply all terms by 2. 2 times k plus 1 over 2 plus 2 times k plus 1 equals 2 times k plus 1 times k plus 2 over 2. We're just multiplying everything by 2 to clear fractions out. So those cancel, those cancel. So I would be left with k times k plus 1 plus 2k plus 2 after I distribute. Equals k plus 1 times k plus 2. If I distribute some more, I would get k squared plus k plus 2k plus 2 equaling k squared plus 2k plus k plus 2. Well, notice the expression on the left is equivalent to the expression here on the right, and so we can conclude, therefore, by induction, 1 plus 2 plus 3 all the way out to n is simply equal to n times n plus 1 over 2. So that proves this result. Okay? If I return back to the notes, so that was B. Let's take a look at another induction example. So use induction to show that 1 plus 4 plus 7 dot dot dot. So if we notice this pattern right here, I'm starting with 1 and I'm skipping and doing every third digit after that. Plus all the way up to 3n minus 2 is equal to n times 3n minus 1 over 2. So I wish to show this using induction. So let's do another example. So prove 1 plus 4 plus 7 all the way out to 3n minus 2 is equal to n times 3n minus 1 over 2. Okay, so proof. By induction, and I must always do the base step. That is, show true for n equals 1. So 1, that should equal 1 times 3 times 1 minus 1 all over 2. That's 1 times 3 times 1 is 3 minus 1 is 2 over 2. That's 2 over 2, which is 1. Okay? So now we write up our inductive hypothesis, which I will just abbreviate IH, and I get to assume that this is true for all n equals k. That is 1 plus 4 plus 7 plus 3k minus 2 is equal to k times 3k minus 1 over 2. And it's important that I get to assume that this is true. I haven't proven anything yet, but for the benefit of the doubt, I'm going to assume that my inductive hypothesis is true and then move to the induction step. Which is that we must show that this is true for k plus 1. That is 1 plus 4 plus 7 plus 3k minus 2 plus, now the idea is I notice I'm adding 3 to each one, and so this would be 3 instead of a k. This is k plus 1 minus 2. Well, let's run through this and let's begin to see what occurs. So this right here is my inductive hypothesis. So by the inductive hypothesis, what does this sum up to? 1 plus 4 plus 7 all the way out to 3k minus 2. Well, by the inductive hypothesis, this sums up to k times 3k minus 1 over 2. So I'm going to write that. Instead, so k times 3k minus 1 over 2 plus, I'm going to clean up this piece over here algebraically. This cleans up to 3k plus 3 minus 2, so that would be 3k plus 1. And now let's just do some algebra. Let's add these together. So add, if I wish to add these together by, so adding fractions, I can get a common denominator then of 2. This numerator stays the same, so k times 3k minus 1. I multiplied into 2, so this has to multiply by 2 in the numerator. I can copy down that common denominator and now simply have k times 3k minus 1 plus 2 times 3k plus 1. Let's see what this gives us. Okay, so if I clean this up, I'm going to have a 2 in the denominator. K times 3k, so that would be 3k squared minus k. K squared minus k plus 6k plus 2. Which then I could write as 3k squared plus negative k and a 6k, that's a 5k plus 2 over 2. And now if I factor 2 in the bottom, if I factor this 3k squared plus 5k plus 2, this factors into 3k plus 2 times k plus 1 over 2. Which, if we notice, I can rewrite as k plus 1 times 3 times k plus 1 minus 1 over 2. This 3k plus 2 is the same as this right here, okay? Which proves the result. Thus, by induction, 1 plus 4 plus 7 all the way out to 3n minus 2 is equal to n times 3n minus 1 over 2. So that was our second example that we introduced using induction. Let's take a look at one that involves a sum of a geometric series. So use induction to prove the sum of a geometric series is given as follows. So the sum from I equals 0 to n of r to the I, which is just r to the 0 plus r to the 1 plus r to the 2 all the way out to r to the n. Our claim is that this is going to sum to r to the n plus 1 minus 1 all over r minus 1. So let us tackle this guy by induction. Okay. So prove the sum from I equals 0 to n of r to the I, which is r to the 0 plus r to the 1 all the way out to r to the n, is equal to r to the n plus 1 minus 1 over r minus 1. So prove by induction. So first and foremost, we do the base step. We show that this is true for, in this case, n equals 0. So r to the 0 is equal to r to the 0 plus 1 minus 1 over r minus 1. 0 plus 1 is 1, so this would be r to the 1. So r minus 1 over r minus 1. I have a numerator and a denominator, which are the same thing, and so this equals 1. And if we recall from elementary algebra, if I take any base and raise it to the 0 power, it always equals 1. So this is true. So the base case, or the base step holds. Okay. And so now let us write up the inductive hypothesis. And so we are going to assume that this is true for all n equals k. That is r to the 0 plus r to the 1 plus r to the 2 all the way out to r to the k equals r to the k plus 1 minus 1 over r minus 1. And it's important that I get to assume that this is true. So I can use this relation, and this happens a lot during inductive proofs. I'll have this r to the 0, I'll have this long expression right here, and then I will substitute in what it equals by using this inductive hypothesis. So let's move on to the third step, the induction step. We now show true for n equaling k plus 1. That is r to the 0 plus r to the 1 all the way out to r to the k plus r to the k plus 1 needs to equal r to the k plus 1 plus 1 minus 1 over r minus 1. I need to show that this is true. Okay? Well, take a look at these first, I guess, k plus 1 sums. R to the 0 plus r to the 1 all the way out to r to the k. This is the inductive hypothesis. So by the inductive hypothesis, I get to assume that r to the 0 plus r to the 1 all the way out to r to the k sums up to r to the k plus 1 minus 1 over r minus 1. So I can substitute that in for this long series of things that I'm adding right here. So by the inductive hypothesis, this sums up to r to the k plus 1 minus 1 over r minus 1 plus r to the k plus 1. Okay, and I would like to try to add these together, and the goal is to try to make them see if it's equivalent to this right-hand side right here. So what I'm going to do next is I'm going to multiply top and bottom over here by r minus 1. The goal is I want to try to add these fractions together. So this r to the k plus 1 minus 1 over r minus 1 plus, if I multiply in top and bottom of this last term by r minus 1, then I will have r minus 1 times r to the k plus 1 over r minus 1. Now remember, in order to add fractions, I just copy down the common denominator, and I do have a common denominator, which is r minus 1. So let's continue that over. So r minus 1. And so it's simply numerator plus numerator. So the numerator in this first fraction, r to the k plus 1 minus 1. Plus the numerator of this second fraction, r minus 1 times r to the k plus 1. And all of that is over r minus 1. Okay, well, let's do a little bit of algebra on this guy. This is r to the k plus 1 minus 1. Now, if I take this r to the k plus 1 and distribute him in, then I would have plus r times r to the k plus 1 minus r to the k plus 1 all over r minus 1. Well, if I take a look a little bit in this numerator, this r to the k plus 1 and this negative r to the k plus 1 are going to cancel. For these two that are multiplied together, this is r to the first times r to the k plus 1. So if we remember from algebra, I keep the base and I add the exponents. So this is k plus 1 plus 1. This minus 1 is outside of the exponent over r minus 1. Okay. This then becomes r to the k plus 1 minus 1 over r minus 1. And if I recall, is that what we wanted to show? It is. I wanted to show that all of this sums to r to the k plus 1 minus 1 over r minus 1. So this proves the desired result. Okay, lastly, I think there's one more proof that I want to take a look at. And this is called the handshaking theorem. So the handshaking theorem says this: okay? Use induction to prove if n people shake hands, then the total number of handshakes is n times n minus 1 over 2 for n bigger than or equal to 2. So let us see if we can't prove the handshaking theorem. Okay. So, for lack of a better statement, for n people the number of handshakes is n times n minus 1 over 2. I guess I'll say for n greater than or equal to 2 people. Be kind of silly to shake hands with yourself. So for n greater than or equal to 2 people, the number of handshakes is n times n minus 1 over 2. So let's do the proof, and we will do it by induction. And so first, we look at the base step, and in this case, we are going to show true for n equaling 2. Okay? Would make sense to have n equal 1. And so let's show that this is true for n equal 2. So the number of handshakes would equal 2 times 2 minus 1 over 2. That's 2 times 1 over 2. That's 2 over 2, which equals 1. Now, notice this is correct. For n equaling 2 people, 1 handshake occurs. When I shake your hand, we're 2 persons, but there's 1 handshake. Now, let's write up the inductive hypothesis. The inductive hypothesis I'm going to assume that this is true for all n equals k. That is, the number of handshakes is equal to k times k minus 1 over 2. And I get to assume that this is true. Now, we move on to the third step, the induction step. We now show that this is true for n equaling k plus 1. So, for k plus 1 persons, the number of handshakes would equal k plus 1 times k plus 1 minus 1 over 2. Now, if I clean this up a little bit, the idea is instead of, I'm looking at this inductive hypothesis, which is k times k minus 1 over 2, but instead of writing a k, I'm just writing a k plus 1. Okay? So the number of handshakes will be k plus 1 times k plus 1 minus 1. This then would equal k plus 1 times k over 2. And if I rearrange, that's k times k plus 1 over 2. Okay. Now, I'm going to pause right here and consider. Okay. I'm going to put this guy here in a little red block. And simply consider this. Okay? let's consider the number of handshakes for K people. And by the inductive hypothesis, that is K times K minus 1 over 2, plus the K plus first person must shake K hands. So imagine all the first K people have shooken hands, and a K plus 1 person comes along. Well, in order to shake everyone's hand, he or she must then shake K people's hands. So plus K. So let's see what happens when I add these two together. In order to add, I get a common denominator. So this would be K times K minus 1 over 2 plus 2K over 2. Which would be K squared minus K plus 2K. That's K squared plus K over 2, which is K times K plus 1 over 2. Now, I told you to recall, or at least make a note, of what was in this red box, which in fact was what? K times K plus 1 over 2, which is exactly the number of handshakes that would be given for K plus 1 persons. So this proves the result. And so that's an introduction to mathematical induction.